Why are some things solid, others liquid, and some gas? It all comes down to atoms and most importantly, their electrons. Picture an atom like a tiny solar system, a nucleus at the center, with electrons zipping around. The number of protons defines the element, but electrons decide how atoms interact. These interactions determine if atoms cling together as solids, flow as liquids, or fly apart as gases. Scientists compare elements at standard conditions, room temperature and normal air pressure, because changing these can turn solids to liquids or gases to liquids. The key is energy. Atoms want to be in their lowest, most stable state, arranging their electrons accordingly. Strong electron bonds make solids, weaker ones make liquids, and almost no bonds mean gases. So, the state of matter isn't random. It's a direct result of atomic structure and electron behavior. From helium in balloons to gold in rings, it's all about how electrons arrange themselves and interact. The world's diversity of matter is written in the language of electrons. Meet the noble gases, the ultimate introverts of the periodic table. Take helium. It makes balloons float, but its atoms don't interact with anyone, not even each other. Helium's 2 electrons perfectly fill its only shell, making it stable and uninterested in bonding. With no need to share or steal electrons, helium atoms float around solo, which is why helium is always a gas. The same goes for neon, argon, and the rest of the noble gases. Their full electron shells make them chemically noble. They rarely form compounds. This self-sufficiency is why they exist as gases at room temperature. When you see a helium balloon, you're witnessing quantum mechanics in action, countless stable, independent atoms, too uninterested in each other to become liquid or solid. Noble gases are born with everything they need, so they remain free-spirited, floating as gases. Their aloofness is the secret to their gaseous state. It's a simple, elegant explanation for why these elements choose to be gases. The noble gases are the royalty of the periodic table, content, stable, and alone. That's why they float away, untouched by the world around them. What about the air we breathe? Mostly nitrogen and oxygen. Unlike helium, these atoms don't have full shells. Their solution, the buddy system. Oxygen pairs with another oxygen, sharing electrons to form O2. Nitrogen does the same, forming N2 with an even stronger bond. These diatomic molecules are stable and satisfied, much like noble gases. The forces between O2 or N2 molecules are weak, so they don't clump together as liquids or solids at room temperature. Instead, they bounce around freely, making air a gas. Nature's clever fix. If an atom can't be stable alone, it finds a partner. That's why 99% of the air is made of these stable pairs. Only at very cold temperatures do their weak attractions pull them into liquids. The buddy system keeps our atmosphere light and breathable. Stable pairs, weak attractions, and lots of freedom. That's the secret of air. It's a beautiful solution to the quest for electron stability. Why is iron a strong solid, while mercury is a liquid at room temperature? The answer: electrons. In iron, outer electrons are shared among many atoms, forming a C that glues the atoms into a rigid crystalline structure, making iron hard and solid. Mercury, however, has a full outer shell, making its atoms reluctant to share electrons. This results in weak metallic bonds, just strong enough to keep mercury from becoming a gas, but not enough to make it solid. Mercury's heavy atoms also experience relativistic effects. Their electrons move so fast, they're pulled closer to the nucleus, making them even less available for bonding. The result? Mercury stays liquid, while iron stands strong. It's all about how willing atoms are to share their electrons. The metallic glue is strong in iron, weak in mercury. That's why one builds skyscrapers, and the other fills thermometers. Why do most metals shine with a silvery luster? It's all about electrons and light. Metals have a sea of free electrons that can't absorb visible light photons. They need more energy than visible light provides. So, visible light bounces off, reflecting all colors at once, which our eyes see as silvery or white. That's why aluminum foil, steel spoons, and silver coins all gleam. The same electrons that make metals solid and conductive also give them their shine. Only high-energy ultraviolet light can be absorbed. Visible light is simply reflected. This perfect reflection creates the classic metallic sheen. The secret to a metal's shine is its sea of electrons, always ready to bounce light back. If most metals are silvery, why is gold golden? The answer: relativity. In gold, relativistic effects pull electrons closer, shrinking the energy gap so gold's electrons can absorb blue light. When white light hits gold, blue is absorbed, and the remaining colors, yellow, orange, red, reflect, giving gold its warm hue. Gold's color comes from what it takes away, not what it adds. Copper is similar, absorbing blue-green light for its reddish tint. Some gases are colored for the same reason. Their molecules absorb certain visible photons. Fluorine absorbs violet, appearing yellow. Chlorine absorbs blue-violet, appearing greenish-yellow. Nitrogen, oxygen, and noble gases are colorless because only ultraviolet light can excite their electrons. Visible light passes right through. The color and state of matter all come down to the dance of electrons and light. Science is cool.